Well, welcome back for week 2 of Cave and Karst in Missouri. Today I'm here to talk about an introduction to karst geology. We're going to really talk about different karst rocks. And the first thing I'm going to say is there are 2 rocks that dissolve very easily in water. And because karst, which is this word that we use for these kind of landscapes, but caves and sinkholes to many people, are formed where the rock has dissolved out the water. There's other ways to get caves like lava tube caves and things like that, but what we really are focused on in this class and in our discussions is rock that has dissolved by the action of water, and it's water with a mild acid or a little weak acid in it. And I'll explain that, but the 2 rocks that dissolve most easily are limestone and dolomite. And I've brought with me today a piece of limestone. Just kind of gray, average looking limestone that's very common around here. I'll talk about this more in a few minutes and I'll show it more in a few minutes. But it's made of the mineral calcite, which is this little squashed over cube in my book. It's rhombohedron if you're into the mathematical or geometric figures. And that means it forms these very nice crystals. It's fairly soft. It has a hardness that's about as hard as your fingernail. That's because it's made mostly of calcium, like your fingernail. Calcite is actually, in a chemical formula, calcium carbonate, which if you're into chemistry symbols is Ca, capital C, little a for calcium, capital C for carbon, and 3 oxygen. So it's CaCO3, where O is the oxygen atoms, the C is the carbon, and the Ca is calcium. And if you think about that, it's not that hard to think about. Calcium carbonate is really Ca and O, oxygen, plus an H2O plus a carbon atom, and the H might just bubble away because that's hydrogen gas. So if you think about calcium carbonate and H2O, it's pretty easy to think about getting hydrogen or water molecules, carbon dioxide molecules, and then just calcium and oxygen. So that's kind of why we talk about these rocks as dissolving. And dolostone, which is made up of the mineral dolomite, and so sometimes we just refer to it as dolomite, is a lot like calcite. It's the same carbonate at the end, the CO3 at the end of the molecule, but some of the places where calcite would have calcium, dolomite has magnesium. So its chemical formula is calcium magnesium CO3. And so, as you might guess, that too dissolves in water. So that's kind of how we're starting forward. And the karst geology is mostly about rocks that are dissolving in water. So first I want to take a minute and think about, now that we've talked about some of the minerals and the rocks that come from those minerals, what those are made of, let's talk about the water for a second. As water, rainfall, H2O, falls through the atmosphere, I think most of us know that our atmosphere, we breathe in oxygen and humans breathe out carbon dioxide, trees breathe in carbon dioxide and breathe out oxygen. And, we've heard things like that maybe all the way back in elementary school science. As simplified as that is, what it does tell us is there's a lot of carbon dioxide in the atmosphere. The atmosphere is made of nitrogen and oxygen and carbon dioxide and all of these other gases. And so as droplets of water fall through that, they pick up some of that carbon dioxide. They dissolve it, much like there's carbon dioxide dissolved in soda water. And when that rain lands on the land surface, it's either going to run off the surface or soak in. And we know that what runs off forms lakes and streams and rivers, but let's talk about what soaks into the ground because that's probably where it's going to see the rock. So we call that groundwater. If you think of a sponge, we have water that, if you sprayed water on a sponge that's been very dry, bit by bit you'll see the sponge kind of get damp and then expand and stretch out. And water does the same thing as it soaks into the earth. It fills up the holes between the grains of the soil and the rock. And most of us don't like to think about that what we walk on is, not solid rock, but it is solid rock. But most rock has tiny microscopic holes in those. We call those pore spaces, just like you and I have pores on our skin. And so when we're looking at water that's underneath the surface of the earth, we are looking at the rocks and the soil and whether those pore spaces have air bubbles in them or gas from plants and bacteria in the soil or water in them. And so that gives us a couple of different options to think about. The first one that we think about then is if all the holes in the rock are full of water, we would call that, like a sponge that's full of water, saturated. And so we call that the zone of saturation. That's the zone where all the pore spaces in the rock or the soil are completely full of water, and so it's holding all the water it can, and there's no more air left, or maybe a few stray air bubbles in there, but really it's just full of water. And then above that, if you think about how water seeps into the ground, soaks into the ground, you get to a point where somewhere above the water saturation is an area where some of the pore spaces are full of water and some of them are full of air. Many of them are full of air, 50% or so. And that is what we call the unsaturated zone. So it's kind of those rocket science terms here. If I fill all the holes in the rock or the soil with water, we call that saturated. If a significant number of the holes are not full of water, we call it unsaturated. And those are pretty simple terms. We sometimes use old-fashioned terms for them. Early in the days of science in the 1800s and early 1900s, people would sometimes use the words phreatic, meaning circulatory system, for the zone of saturation, because that's where the water was filling all the holes and moving around side to side. And they would use vadose, V-A-D-O-S-E, as another word for unsaturated. In either case, we're going to really try to stay with unsaturated and saturated here. But what we're also going to say is where those two meet, where the unsaturated and the saturated meet, is a word I bet you've already heard before, and that's called the water table. If you live anywhere that you have a water well, or you've heard people talk about the city water wells, the water table is dropping in a drought, that's what they're talking about, is where the saturated zone has met the unsaturated zone. We call that the water table. It's not a table, it's just a layer in the earth that we can look at and say, this is where below this, all the pores in the rock or the soil are full of water, and above it, they're not all full of water, and that makes a difference if I'm trying to pump a well. So that gives us a saturated zone, a water table, and an unsaturated zone. And how does that look? Well, I'm going to give you a picture that's usually easy to see when you think about the water table, easy to see it. And if you think about it, typically the water table is sort of a subdued version of the landscape, the topography. So we think of high hillsides and low valleys, and the water table usually is lowest below the valleys and highest below the hillsides as water soaks in. And if you think about a sponge or maybe a giant furniture cushion like the sofa I'm sitting on, if I spilled water on it and had a low spot in it, the water would tend to accumulate in the low spot and would soak into the high spots and go there. And so, you know, looking at the figure, you can sort of figure that out. The other thing is sometimes that water table actually intersects the land surface, actually shows up right where the land hits a low spot is also where the water table is. If the water table is intersecting the land surface, that's going to mean water is coming from the water table, from the saturated zone, out into the open air in like a valley floor, and you and I would call that a stream or a river. In fact, we'd probably call that a perennial stream or river if it's intersecting the water table and there's constantly water flowing out. We'd call it a seep or a spring where the water does that. So those are some of the key terms that I want us to learn today. We're going to think about the water table. It varies. It's not a specific set number. As I mentioned earlier with cities that have water wells, if I have a drought year, if I have a dry period in my year, if I have a couple of months that are drier in the summer and wetter in the winter, then typically the water table drops during the driest part of the year, even just because plants might absorb some of the water with their roots. And during the rainiest part of the year, or when snowmelt is, or whatever I have like that, when I have more precipitation, I'm typically going to have more water and the water table will rise, actually. So the water table moves up and down a little bit through the different seasons, through decades of drought or multiple year droughts and multiple wet years, or big storms like hurricanes. And it usually follows somewhat the surface topography. It usually is tallest or highest elevation of the water table underneath hilltops and lowest elevation underneath valley bottoms, or right at the valley bottom. So that gives us a little bit of thing to think about. It brings us back then, now that we've talked a little bit about saturated and unsaturated and water table, now that we've thought about the water that soaks in and picks up a little bit of carbon dioxide, and oh yeah, water with a little bit of carbon dioxide is what we call carbonic acid. And you would know that because that's like carbonated water, or it's even like soda if you drink the sugary sodas, like the various cola brands. Those are things that are made of sugar and water, which makes it a thicker, goopier, we call it syrup usually, and the syrup is thick enough to hold even more carbonation in, even more carbon dioxide. Regular soda water can hold a certain amount of bubbly, fizzy carbon dioxide in, and natural waters out in springs and caves and streams also holds a certain amount that's related to how much is in the atmosphere. So now that I've got that, I've got these waters moving through the holes in the rock, and they soak from hole to hole like going through a sponge. They can squeeze from pore to pore, and they are carrying a little bit of water, but a little bit of acid. We call those very mildly acidic. It's not like vinegar, it's not like battery acid, it's just very, very slightly not a neutral 7 on the pH scale, because the pH scale from 0 to 14, we consider 7 perfectly neutral. So now that I've got the water thought about, let's go back to the rocks a second. And rocks that are made of different things react differently. We've already talked about limestone that reacts very well with water and dissolves because it can actually fizz out some of the carbon dioxide in that slightly acidic water. There's other things though, like shale or mudstone, that's made of clays and little very fine particles of quartz. And so shale and mudstone usually don't let water go through them very much. So in the words of science, when we have a saturated zone, we call it an aquifer. But if it's saturated things like clay or mudstone or shale that just don't let the water move very quickly through those holes from hole to hole, we call that an aquitard. It's something that delays or slows down the movement of water. So now we have aquifers that freely transmit water from pore to pore to pore, and then we have aquitards which slow down the movement of water from pore space to pore space, and those are made of different rocks usually. And then one more rock that I'm going to introduce is the mineral quartz. It's one of the most common minerals on Earth. Some people see it in quartz crystals, those lovely hexagonal prisms that you can buy in many jewelry stores or curio shops. But it's also just blobs like this. It's the same kind of thing that window glass is often made of. When you melt sand, which is also very rich in quartz usually, you get a thing that doesn't have any what we call cleavage. It doesn't break along the flat specific planes like a block of calcite. It breaks along just kind of curved, shiny, waxy, glassy surfaces, and that's called quartz. Quartz is very hard. It will scratch glass. It's much harder than calcite. Calcite's very soft and will react very well with water. So that gives us, especially in Missouri, two different rocks. First, we had the limestone that I mentioned, and it is made of small grains of calcite. And then we had the chert that I mentioned, and that is made primarily of small, very microscopic grains of quartz. And chert tends to occur in lots of the rock layers here in Missouri, but sort of is a different thing than the limestone, than the calcite. And so it may be a different layer and the water moves through it differently as I go from one layer to another, or may even not move through the chert at all or the shale. It may back up and spend more time dissolving the limestone. Why do I say that? Well, if we take a dilute hydrochloric acid and put it on just a few drops of it, this is a 5% hydrochloric acid solution. I'm going to put just a few drops on the limestone. And if you can see it, it fizzes. It's fuzzy and foaming, just like pouring a can of cola, opening it up and pouring fresh cola in a glass, and you get that frothy foam and fizz. And that's the carbon dioxide fizzing out. This is dilute acid that's a little more strong than rainwater, and so it reacts more vigorously with our limestone. But we're doing that so that you can see that that's what's really going on over much longer, slower periods of time. Even though it's not as aggressive and vigorous a fizz, the rock is having this groundwater move through it, and bit by bit it's dissolving and releasing bits of carbon dioxide gas and carrying away bits of calcium and H2O in there. That's where I'm going to stop for right now, and we'll come back and look a little bit later with some more components of this.